Okay. So this variance is insensitive to differences between means. Let me elaborate a little bit more. What this means is you've got, how did we calculate variance? Do you remember how we calculated variance or S squared in general in t-test of independent means? What did we do? Very good. Very good. Sum of squared deviations. Perfect. Exactly. Thank you very much. So sum of squared deviations divided, so S squared was the sum of squared deviations divided by degrees of freedom. Okay? So this method, actually, of just summing the deviations and dividing by the degrees of freedom gives you estimates of the variance. And if you basically take the average of these variances, let's say you have three groups. You know, S1 gives you the X1, M1. S2 will also be the sum of squared deviation of the second group, degrees of freedom 2. This is 1. S3, oops, is also going to be the same thing, but done for the third group. And in fact, that's exactly what we did last week. We did this thing where we had these groups, these samples here, sample 1 and sample 2. Sorry, this would be 1 and 2. And we took the variance, we calculated the variance, and then we estimated the variance of the original population. This one, S squared 1. And we estimated the variance of S squared 2 by using the variance here, the sum squared deviations divided by degrees of freedom of the second group. So that's what we did. And we can do it a third time for the third group. So the only difference here would be that we'd have a third group. I don't think it'll show on the camera, but here's a third group, just like the second group. And it'll actually also have a S squared or S squared 3. Yeah. So we have three groups. And now you've calculated the variances 1, 2, 3. And this process of actually calculating these variances are insensitive to differences between means. So if this mean was different from this mean, was different from this mean, it won't make a difference in your total sum of the variances here. It makes no difference whether this mean is same as this mean as this mean. It makes no difference. So that's how it's insensitive, in the sense that regardless of what the mean of each of these groups are, it makes no difference in the end result of those variances here. And what did we do with these variances, by the way? After we calculated these variances, what did we do with them? When we calculated, remember, so look at the steps. So you've got the sample, and we went up to the variance, and then we went from the variance to pool them. Exactly. So we pooled them. So when we pooled them, we took this variance, and we weighted them and pooled them. Now we're going to pool them again, but we're going to pool the three of them. And since we're in an introductory class, I'll never give you unequal ends, meaning the samples will always have the equal sample sizes. When you have equal sample sizes, if you had these two groups equal in sample size, when you pull them, what did you really calculate? The mean, exactly. So when you have equal ends, your variance, the pooling of your variance is just going to be the mean of these variances. So S squared pooled, if it was two groups, it would be S will be equal to S squared 1 plus S squared 2 divided by what? By n. Oh, no, not by n. Divided by 2. Divided by 2. Right? That's the mean. Right. So let me repeat again. So if these groups were equal in size, each one of the variances will be multiplied by half. Remember, we just talked about that, how pooling, when you pool groups that have the same sample size, you basically take the average. So your degrees of freedom 1 over degrees of freedom total would be just simply a half. So that would be s squared 1 plus 1 and a half s squared 2. So this would be, 1 times s squared 1 over 2 plus 1 times s squared 2 over 2, which gives you s squared 1 plus s squared 2 over 2, right? Which basically is just the natural average of these two values. Okay. So where did I lose you? The half thing. Okay. So as we talked about when we were looking at the test, we said when you're when you're pooling equal sample sizes, your degrees of freedom 1 will be actually simply half the degrees of freedom of your total degrees of freedom. So let's say you have, let's say here in this sample you have 5, n equals 5, and n equals 5. These are equal sample sizes. What will your degrees of freedom be here? 4. Okay, so degrees of freedom 1 would be 4. What will your degrees of freedom be here? 4. Okay? So if you wanted to do the long step of degrees of freedom 1 divided by degrees of freedom total, okay, times S1 plus degrees of freedom 2 over degrees of freedom total times S2, what will this be? What will this weight be? It'll be 4 over 8. 8 is the total degrees of freedom, 4 plus 4. So 4 over 8 is half. And similarly, this will also be 1 over 2, 4 over 8, times s squared 2. And this is s squared 1. So this is where, James, is that clear now?
Yes.
Okay. So basically, I'm just deriving how, in fact, when you're looking at two samples of equal size, your s squared pooled will simply be the average. Will simply be the average of these two variances. Now, if that's the case, if your s squared pooled will simply be the average, what would be s squared pooled for the 3? Any guesses? It would be, it'll be s squared 1 plus s squared 2 plus s squared 3 divided by 3. Exactly. Average. Whenever you average anything, you take the value of number 1 and number 2 and number 3, and you divide it by the number of items you have, the average. Remember, average, mean equals sum x over n. So you sum s1 plus s2 plus s3, that's your sum of x, divided by the number of scores, and that's 3 scores, so that's n, that's 3. So that's your s squared pooled. Now, Fisher basically said, hey, look, this variance, this s squared pooled, is insensitive to differences between means. And he gave it a new name. He called it s squared within. I'll explain why it's called within in a little bit. But for now, let's just accept its new name. He called it s squared within. And as I said, s squared within is insensitive to differences between means. Everybody okay with that? Meaning that if these means start to differ from each other, it won't make a difference in the sum here. It makes no difference. Now, what's really brilliant, Fisher, this was there. Everybody understood this concept. But what was brilliant is he came up with another technique of calculating variance. He wanted to calculate the same variances of three populations. And he came up with a technique that if he used the variances from the samples, if the sample mean starts to differ, then that variance will start to grow. So that variance is sensitive to differences between means. He came up with a way to calculate variance, different from this way of calculating it, that is sensitive to differences between means. He called it S squared between. Okay? And as I said, S squared between is sensitive to differences between means. To explain what that means, sensitive to differences between means, let me again reiterate what it means to be sensitive to differences between means. It means that if the means start to differ, if the means are different, then the variance will grow. It'll become bigger and bigger. That's what sensitive to differences between means means. If the means differ, the variance starts to increase. So it's actually taking into account the differences between means plus the natural variance within each of these samples. Okay, so he came up with these two different ways of calculating variance. And one of them is insensitive, and one of them is sensitive between differences between means. And he decided, look, I can come up with a ratio that will change based on whether the variance is actually will change. He came up with a ratio that would change in value when the means are different and become bigger and bigger as the means start to differ from each other further and further. When the means start to actually be different. So look at these three means. Okay, so we have group number 1, 8, group number 2, 10, and group number 3, 16. These are their means. Okay, this is M1, M2, M3. Now, these means are different, right? These means are different. We don't know how different they are, but we can tell they're different, right? They're different numbers. Now, given that the fact that they're different, okay, what we'd expect is that this way of measuring the S squared between, this way of measuring will actually be different from this way of measuring it. So if we calculate the variance from these three groups, this will be different from this. And we'd expect this to actually be bigger, because the more different the means are, the bigger that this variance will grow. It'll become bigger and bigger. Okay, so let me put it in more maybe formulaic ways. So he decided, look, I'm going to create a ratio, and this ratio is S squared between divided by S squared within. Okay? And we understand that S squared between takes into consideration the variance within each of these groups plus the variance that the fact that the means are different add to it. Actually, maybe I should explain the S within first, because it'll be easier to grasp. S within is basically just the sum of the variances within each of these groups. That's why it's called within. So it's simply the sum of the variance of this plus this plus this, okay, divided by 3. I should have said the average of the variances here. So it's just the sum of these divided by 3, i.e. the average. Here it is, right? So it is this plus this divided by 3. It's simply the within group variance. This is the term we use, the within group variance. Everybody with me on that? So in a way, it doesn't matter where the mean of this guy is and where the mean of this guy is and where the mean of this guy is. This could be 8, and this could be 10, and this could be 16, or this could end up being 100, and it makes no difference because all you're measuring is this little variance inside. Okay? And this gives you S squared within. It's the measure of variance that's insensitive to differences between means. Everybody with me up to now? Anybody lost? No lost. Fantastic. That's the easy part. Now, the